All right. So in the last class, we discussed the ferroelectric memory, ferroelectric capacitor-based memory. We discussed how to read, basically how to write it, essentially. We didn't get a chance to get into the read to that level of detail, right? Do you guys remember how to write into a ferroelectric capacitor-based memory, FE-cap? So you have a ferroelectric capacitor in series with a transistor. What you do is you apply appropriate voltages to these two interconnect lines, either VDD here, ground on the other side, or vice versa, right? And then based on the polarity, based on the direction of the applied voltage, you have either positive polarization stored or negative polarization stored in the ferroelectric material, right? That was a very simple enough write approach. But let's talk about reading approach. Okay, how do you read? Did we discuss the capacitance versus voltage characteristics of a ferroelectric material? Folks, do you remember? We discussed that if you take dq over dv, you get the capacitance, right? And polarization was nothing but charge. And if you do so, in this region, the capacitance should be flat, almost like very small, not zero, of course, but very close to zero. So here you have low capacitance, but in this region, you have really high capacitance. So you have a spike. And then again, after it saturates, you have low capacitance. So if I draw the capacitance, you basically have low to spike and then low again. And same applies to the other side here. Okay. So now setting that aside, let's discuss how do we read. So when you read, you apply a certain voltage. Okay. And you try to notice, let's consider two scenarios. You either had this positive polarization stored or negative polarization stored. Okay. And I'm going to apply a voltage of this much, like maybe 25 volt or something. I know the numbers are crazy, but just bear with me for a second. Okay. This is what we could possibly do. So if you were storing this positive polarization, then with this voltage, which path will you follow? The top one or the bottom one? The top one, because you are already in the positive polarization region, right? So you will go through this route. Notice, no matter how high of a voltage you apply or how low of a voltage you apply, will the capacitance level ever be too high? Wouldn't it be really flat? You guys all agree with me? Because you don't go through this transition region. As long as you don't traverse through that transition regions, your capacitance will be pretty benign. Will change slightly, but not much. Does that make sense? Okay. Okay, so you get some, you guys know the current flowing through a capacitor is this. So you have a like low enough capacitance, you have a low enough current. It's almost linear. Okay. Now, let's assume that you are storing negative polarization right here. For the same level of applied voltage, what happens now is you go through this route. Does that make sense? So you observe and experience a spike in capacitance. And a spike in capacitance will lead to a spike in current. So basically, when you read, you either get a spike or you don't. And you basically sense whether there was a current spike or not. Simple. Okay. That's what you sense. And you can remember in the very first few classes we discussed that you have to be able to electrically read, electrically sense stored data. That's the main criteria, right? Sure, ferroelectricity has a property of storing charge, which you could electrically read using current spike. So there you go. Anybody notices any challenge or problem with this approach? Anyone? Yes. It's a good point. Imagine that by doing some interesting circuit design, we can capture that. Okay. I can give you a circuit which captures the spike. Even then, there is a challenge. Yeah, there is, because you know which ferroelectric you are using. Okay. And you can test out, this is a polarization versus voltage characteristics of a standalone ferroelectric that you put in. Is it PCT? Is it HZO? You know it beforehand. So you know the coercive voltage of the, so you know how much voltage to apply to get through. Yes. Yes and no. Yeah, we like to have a certain magnitude, because if it is too high, then it will probably burn down few things. But that's not really it. No, we made sure to only apply positive voltage. Remember, by switching from, let's see, VDD 0 and VDD 0. So we didn't apply VDD and negative VDD ever, right? We just basically flipped the source of the voltage. Okay. I'm glad that you're trying. Keep trying. Yes. That's an interesting point. It's not really instantaneous because it's a capacitor. It takes some time to change. Yeah, it's close enough. You're right. But it's not really the problem that we're looking for. We can handle all of this in one circuit or the other. There is a more serious issue with the read operation that you should uh, worry about. Okay, which path am I following when I'm reading? This one or the other one? Both, actually. So depending on what was stored, right? If it was storing A, then you traverse through this path. If it was storing B, you traverse through this path. You don't know which one will be traversed, right? Because you don't know what was stored. You're trying to sense what was stored, and your material will take one path or the other. There is let me give you a hint. There is a problem with one of the paths. Let me give you say A to C or B to C. Which path is problematic in your opinion? Is AC or BC? BC. Why is that? You don't like BC? That's why you're... Well, notice, how do you write into ferroelectric memory? You basically switch polarization from negative to positive, right? Or positive to negative. Notice, while you're reading, you have to go through this route to get the spike. But then when you do so, you have switched the polarization from negative to positive. And then when you remove the voltage, it will get stuck in positive polarization, don't you think? So you've essentially destroyed the stored data. Does that make sense? This is known as destructive read. Yeah, all the other issues are valid, but they're nothing compared to like what you're dealing with here, right? So you basically, this is where you start. You apply a voltage you are going after this region so that you can have a spike in capacitance. But the moment you go through this region, you basically get stuck on the other side. And now you have flipped your stored data. So while reading, you have disturbed the data. This is destructive read, which we try to avoid by at all means, in most other memories. But for ferroelectric capacitor, this is obvious. You have to live with it. Then what do you do? What do you do? Read. We basically, whatever we read, we write back. So ferroelectric capacitor required a write back algorithm, meaning whatever you read, I read 1, so write 1 back. I read 0, write 0 back, something like that. So every read was followed by a write operation, which is a waste if you think about it, right? But it is what it is. Well, what is the advantages? Before telling you the advantage, I want to show you the timeline. Remember, this was in 1950s and 60s when this memory, ferroelectric memory was introduced, right? Let me fast forward here. I was looking for this slide. Okay. So notice this is FE-RAM, ferroelectric RAM, which uses this ferroelectric as a capacitor. And we already discussed the ferroelectric tunnel junction, did we not? That has resistance difference, right? Did you forget from the last class? Okay, there is a recording. So please observe that. And what I will do is I'll make sure to set a new quiz so that you have a quick revision. This will help you in your midterm so that you don't have to revise everything and realize, oh, I didn't really get anything. Make sense? So yes. Right. That's a great point. So I'll tell you. That's why I'm here. So notice we were trying to see the spike. For one kind of polarization, you get a spike. For the other kind, you don't get a spike. You see that, folks? And the spike comes because you switch the polarization. You go through that. Remember that region? You go through this region. That's why you have a spike in capacitance. That's why you have a spike in current. But for the other read, right, within this region, you don't switch. So you don't get a spike. That's why it's pretty benign. And you can now sense between these two lines and see whether or not there was a spike or there was a benign increase or benign change in current. Okay, now it's with respect to time because it's capacitive current. You cannot, it's not a resistor, for example. It changes with time. It will gradually charge up or discharge. So we have to see it with respect to time, and we have to keep in mind how much time we are giving it. So for example, if you sense quickly, if you sense right here, you don't see any difference. So you have to wait until the spike takes place and then stabilizes. And maybe at some point here, you take your sense measurement. Okay, so that's why we show it with respect to time, but regardless. Okay, any problem so far, folks? Okay, we have already discussed this ferroelectric tunnel junction based design. If you don't remember this, we discussed. It's easy for electrons to go over barrier for one case and difficult for the other. And so that was done, and that's the least likely to be used as of now, because there are some challenges that people are dealing with in FTJ. And this one is, on the other hand, the most basically common version of ferroelectric memory, because that was commercialized even. At some point, it was commercialized. And despite these challenges, we are talking about decades ago when this was commercialized. So then we didn't have to deal with billions and trillions of storage cells. We needed something non-volatile. We didn't have any non-volatile option at the time. And this ferroelectric capacitor seemed like a lifesaver. Make sense? Before we got, into other technologies and invented other options. So now nobody likes it, as you can imagine. Every time you read, you have to write back, who does that? Okay, so setting aside, getting back to more recent times. And this is actually one of the most cutting edge ones for ferroelectric memories. And these are the ones you should care about moving forward. This one and the next one that we will discuss. And this will take me into a territory that requires some really serious tangent. But they are worth taking, because how many of you have heard about negative capacitance? None of you. Some of you? Negative capacitance? 335 a little bit? Right, thank you. Yes. But most of us haven't heard about it, so I will quickly go over that without trying. I'll try my best not to get into too much detail about it, but I'll try to give you some high-level perspective. So in nature, just take a second to think about, have you ever seen something, a device, a material, giving you negative capacitance? You have seen 2 microfarad, 2 nanofarad, 10 nanofarad, whatever, some numbers, they're always positive. Think of resistors. They're always positive, 100 ohm, 10 ohm, 20 ohm, whatever, but they're always positive. You have never seen negative resistance, have you? What does that even mean? Resistance means that, oh, it hinders electricity. But does negative resistance mean it will help electricity? I mean, how to even physically explain that? Am I making sense, folks? Okay. Interestingly, you can observe both negative resistance and negative capacitance in transient measurements. And here is how. Let me explain. If you take current versus voltage characteristics and you get a straight line like this, what is di over dv? You guys all know Ohm's law, V equals IR. Very simplistic form, right? But actually, the real law should be, you have resistance should be dv over di, or conductance should be inverse of that. Am I making sense? Oh, give me 1 second. What I'm trying to say is, you could represent resistance to be V over I, but to be realistic, it's not really V over I. It should be dV over di. Okay, all with me so far? Okay, so apparently, if you take di over dv, you get the slope, and whatever the slope you get, if you take the inverse of that slope, you should get the resistance. Make sense? Okay. All right. All good. Now, you guys are all with me on this, right? Notice, is this a positive slope or negative slope? If I draw something like this, B, this was A, this is B, is that a positive slope or negative slope? It's always positive, right? Whatever device you have ever studied, BJT, MOSFET, PN junction, think of anything that you've ever seen, or maybe revise your textbooks. You will see every time with respect to current and voltage, when voltage increases, current increase. Simple. You haven't seen a single device that does exactly opposite, except for the 335 folks in tunnel diode. Remember, in tunnel diode, we had a situation where in current voltage, yes, current increases with voltage, but then it does the opposite. And then it takes back to the previous path. So in this region, how do we even explain what's going on here? Notice your current reduces with applied voltage. So if you take derivative here, the slope is positive, and slope, as you see, slope is related to resistance. Inverse of slope is the resistance, right? Folks, am I making sense to all of you? Or don't feel lost. Feel free to ask me questions or stop me. I'm not assuming that everybody has seen this, right? 335 folks may have, but that doesn't mean you have to just put up with that. So stop me if it doesn't make sense. Okay, so in this region, your slope is what? Negative. If the slope is negative, what is the inverse of slope? That's also negative. So that means in this region, you have a negative resistance in transient sense, for example, right? Practically, there are situations where you can have reducing current with increasing voltage. And those regions of operation are characterized as negative resistance. Okay, similar to that, capacitance. Let me talk about capacitance. We just discussed that Q versus V characteristics gives you, if you have dQ over dV, that gives you the capacitance, right? We use that to measure the capacitance for ferroelectric, remember? To take the slope everywhere. But just notice, in a ferroelectric material, just look at the conventional ferroelectric hysteresis. No matter where you go, notice the slope is always positive. Don't you think? No matter where you go, it's always positive. Okay, sure. Ferroelectric material always gives you positive capacitance, it looks like. And so does most other materials. But if I come up with a situation where you have decreasing charge with increasing voltage, so something like that. So basically your voltage increases, your charge decreases. Then we will say we have found negative capacitance. Does it make sense? Just maybe if you have laptop open, or if you could go back home and search, just search for evidence of decreasing charge with increasing voltage. That was a Nature paper. Nature is one of the top journals in the world. And somebody invented it very recently when I was a PhD student, for example, not too long ago. Okay, it's a recent discovery. Negative capacitance was proposed way back in 2008 that it might exist in nature. And if so, then this is what you can get out of it. But it was never officially experimentally demonstrated for a long period. But then people started observing it experimentally. Okay, and when you do so, it's a big nature paper every time. All right. Anyways, where am I going with that? So turns out in ferroelectric material, there is a possibility under certain condition that instead of, just notice as I draw, because after that it will be messy. All eyes on the board. Okay. So instead of switching like this, like going through conventional regular route, it's possible that the ferroelectric material can switch this way. And that came from a mathematical calculation. So when you solve some equations to figure out how the ferroelectric switches, there are three possible solutions. One is this path, the other is the other path, and there was one other mathematical solution that showed, oh yeah, maybe you could go through this route as well. And that was just mathematical. And nobody experienced something like that in real nature, right? Okay, mathematically it's showing it might be possible, but practically no. And that's how many discoveries take place, by the way. People discover matter and antimatter based on this. They say, oh, our equation says there has to be a conjugate of this one, but we never found the other one. Everything looks like this particular version. But then with experiments with persistence, you can find antimatter and antiparticle. You know that, right? Matter and antimatter can annihilate. I mean, if you're watching some sort of science fiction movies and stuff, they use this all the time. But this is reality, by the way. And we have antimatter and matter. But that started exactly like that. There was a mathematical understanding that it might exist, and then people realized it. And so many other discoveries were like that. Gravitational lensing, for example, Einstein proposed in one of his work that that might exist. Gravitational lensing might exist. Relativity, for example, purely mathematical argument. Nobody cared. Hey, doesn't make any sense. Okay, time slowing down, whatever, like length increasing when you move. That doesn't make any sense at all. But mathematically, this is what you get. But then practically, when you do experiments, we use it. For our GPS, we use relativity. You know that, right? We use basically the concept of relativity to make our GPS work. Anyways, getting back to this business. So this is somewhat of a similar situation where theoretically people observe or people realize that there is a path possible to go from negative polarization to positive polarization without taking the regular hysteretic route and this is known as the infamous or famous S curve, because it looks like an S, as you can see, right? And then if the ferroelectric switches like this, then what? Then in this region, notice you have what? Negative slope. That means in this region, you can have negative capacitance. I mean, you may not, okay, well, what's the big deal? Positive to negative, who cares? But if you see the implications of that, and then you'll pay attention for sure. So allow me to explain that to you, okay? Ready? All right. Let's talk about this. Imagine you have two capacitors in series, C1 and C2, and you apply a voltage. You have seen resistance division rule before. When you have two resistors, you apply a voltage, you know how much voltage each of them will get. Similarly, we could use this argument for capacitive division, but it's a little bit opposite to what resistors do. This is what you get. C1 over C1 plus C2 times V. The voltage that you apply. Input voltage. This is input voltage. I guess all with me? Notice one thing. At this point, Vx, so you apply 1 volt. Can you ever get exactly 1 volt or more at the internal node? Is it ever possible? Notice, is it even possible? Why not? Because the denominator is always greater than the numerator. So this number is always less than 1. So the voltage that you get in this node is always going to be smaller than the voltage that you apply. It's common sense, right? Everybody should, hey, whatever voltage I apply, there are two capacitors. One of them will take some share. The other one should get less. So it's never going to be, I mean, forget about being more than the applied voltage. It's never going to be even as much as the applied voltage. There will be some loss. Are you guys all with me so far? So far? Okay. And the stack that I've just drawn, I hope 335 folks can remember. This is basically the gate stack of a MOSFET. Gate. So you have, notice this. You have, forget the ferroelectric. Forget the ferroelectric. You have gate, which is the metal, and then you have dielectric, and then you have capacitance coming out of the semiconductor. So you have two capacitors back to back in the gate stack of a MOSFET. Okay. So apparently what it tells you that whatever voltage you apply to the gate, it doesn't show up at the surface. There was a surface potential in 335. So surface only gets a portion of the applied voltage. Great. If I apply 1 volt, I will get 0.5 max or 0.6 or 0.7. Never 1. Never more than 1. Forget about more than 1. Now, here is the science fiction. Ready to see that? What if this was negative? One of them was negative. Then what? Then all on a sudden, this becomes like C1 minus C2 becomes smaller than the numerator. Uh-oh, what does that mean? If this number is greater than 1 now, if this is greater than 1, that means your internal voltage will be more than the voltage that you apply. Isn't that crazy? You apply 1 volt, but internally you are getting 1.5 or 2 volt. It's being amplified out of nowhere. And that has been a source of like serious debate among physicists, material scientists, engineers. And are you guys all with me so far? Okay. And taking a tangent, for example, when I worked as an intern in Global Foundry, I was put into technology research team where they're dealing with this negative capacitance transistor. And experimentally, we measured and we saw the signature of this thing. And they published papers as well. And there's so much debate. And like, I was right in the middle of it. It was really scary at the time because big professors fighting with each other. This is impossible. This is what you blah, blah, blah. People found alternative explanations to what you observed. But the point is, if you could achieve negative capacitance, wouldn't that be wonderful? And the, the easy way to get the signature of that is to see the amplification of voltage. So you haven't used any amplifier, but you apply a voltage, but you're getting it amplified internally using the internal energy of the ferroelectric material. So that's wonderful. That means your electronics could work with low voltage, much lower voltage. You apply lower voltage, but the material amplifies it and provides higher voltage internally. This is crazy, I know. People couldn't fathom where is this extra energy coming from, right? And there are other energy theories that talks about the domain dynamics of the ferroelectric that gives rise to this extra energy, whatever. It's like, it's a mess, right? I don't want to get into that thing. But do you guys all agree with the fact that if there is a negative capacitance, you get an amplification? Just mathematically. There is no physics or material science there. Just mathematically, does that make sense to you? So wouldn't that be wonderful for electronics if we can actually prove that there is a negative capacitance? Why are you so silent? Okay, so that's exactly what this explains. The example that I gave you, this becomes more specific to the gate voltage of the transistor. So the internal voltage, take a notice. This is a conventional transistor. And the idea was to put the ferroelectric material in series with the gate stack of the transistor. Okay, in series with the gate. In the MOSFET gate, you already have an oxide capacitance. And then you are putting a ferroelectric capacitance on top of it. Okay, so whatever capacitance the MOSFET already provides could be CMOS. And whatever capacitance the ferroelectric provides could be CFE. Does that make sense, folks? Okay. And then if CFE can be negative by going through this channel, this is what you get. You get this ratio to be greater than 1. And by the way, this is taken from a source. If you are wondering why there is a negative sign in front of CMOS, it's because of this. Let me show you. This was positive. The other two was negative. Can I not take this negative as common and then cancel them out? And that's why the CMOS ended up being negative. But practically CFE is the negative one, not CMOS. Did I make sense or not? Okay. All right. So apparently your denominator is smaller than the numerator, and this is a greater than 1 scenario. So your internal voltage, which you get at the MOSFET, is more than what you apply at the ferroelectric terminal. And this is the structure, by the way. You have MOSFET gate, you have ferroelectric material, you have a metal layer, and then you have dielectric, which is hafnium oxide or silicon oxide or something other. Okay, and by the way, why is it so weird? Because it's a FinFET. I mean, you might be wondering, is this a MOSFET? Well, it's a FinFET. This is how it looks like. Have you seen this structure before? Did I try to draw this in class? So this is a FinFET. This is one fin. This is the other fin. Did I tell you that you can only add fins? 1, 2, 3, 4. Okay, that's what. 1, 2, and then maybe if you want 3, 4, and so on. And that's wrapping around the fins. This is the gate. Okay. Are you guys all with me so far? So why am I telling you the concept of negative capacitance? Okay, I know this is a very legit question. How is that even related to memory? Apparently, this phenomena does not only lead to amplification in the internal voltage and make your transistors stronger at lower voltage and thereby make electronics better, it also leads to some interesting design opportunities for memory design. And I will tell you about that. And interestingly, surprise, surprise, it improves SRAM. I mean, if anything, improving SRAM is a big deal, by the way, because we are stuck with SRAM. They're the fastest memory ever. We don't have any alternative to SRAM. If you could make them even better, sure, I will take it any day. And that's what I'm going to show you. And SRAMs have many problems, as you know, with stability, read-write asymmetry, and whatnot. Okay, before getting there, what I've explained so far is only these two figures. Take a look at it. This is the origin of negative capacitance. This is what happens if you have negative capacitance. These figures are only there to help you understand what we mean by CMOS and what I mean by CFE. And the other two figures, this one specifically, I'll explain later. So I'll get back to this figure later. This is a different kind of memory. Okay, using the same structure, if you use negative capacitance mode, you get certain property. If you don't use negative capacitance mode, you get this property. Okay, and get back to this property, which doesn't use negative capacitance, doesn't necessarily use negative capacitance. Okay, but okay, what do you get with negative capacitance, folks? This is exactly the slide that I've just explained, right? Ferroelectric material, S curve, negative slope, negative capacitance. So basically, this is taken from a different source. That's why it looks different. But this is exactly the same thing. I just wanted to add this as well because this has an extra result. Notice this result. How can you see this result and explain that you are getting negative capacitance? What is VG? This is the voltage applied here. Then you have ferroelectric capacitor. Then you have MOSFET capacitor. Two capacitors stacked together. And this is the VMOS or VINT, whatever you want to call it. Okay, internal VX or whatever. And you are plotting VMOS and VG. Notice you are applying VG, but VMOS could be higher than VG. You see that you are getting an amplification in the voltage? Is that clear or not, looking at this data? So that means it's practically impossible. If I ask you to put two capacitors in series, right, the equivalent capacitance will be what? Will be what? You guys remember that? Yes. So if you have two capacitors in series, C1 and C2, the equivalent capacitance will be like this, 1 over C2. Okay, this is smaller than the smallest of the capacitors. Okay, I see some confused faces, so I'm not getting into that, tangent. But at least by looking at this internal voltage versus applied voltage, you see that amplification occurs. And that's exactly what we can use as an argument to potentially use it for certain circuits that could use this boost for, no other extra circuitry. You're getting an amplification for free. All right. And then let's get back to this slide. This is also taken from a source, as you see. I'm going to explain what you get out of this negative capacitance thing. Are you guys ready for it? I use this as a context to answer a question once. Remember steep switching transistor? Steep switching, did I use this term before? Boltzmann limit. There was a question about off current and on current and subthreshold slope. And we talked about people are trying to solve a fundamental barrier, 60 millivolt per decade, which is known as the Boltzmann limit. And our transistors are limited to that. And the way you break it would be to find out interesting physical phenomena that will help you break that limit. And one of the way would be to use negative capacitance. And I'm not explaining how exactly that helps in breaking that limit. Well, maybe you already know. I don't have to explain. So it creates an extra source of amplification. And thereby, it overcomes the Boltzmann limit. Okay? And let me show you this from this data. Let me exaggerate the data first. This is what you get from a standard. Sorry. ID versus VGS. I didn't mean to start from 0. Okay, I meant to start from something non-zero because there is an off current. Okay, do you see that? All right, so this is a standard FinFET or MOSFET, whatever. And now this is critical. Okay, notice as I draw, because that's important. You have to see it in action. Ready? So I start here and then I end here. What do you see in the green one, which is the NC-FET, negative capacitance transistor or something? What do you see? What changed? And I deliberately changed a few things. The initial point, what does the initial point represent? This is the off current, right? When the transistor is off, this is how much current you still have. Notice your VGS is 0, but still there is a current. Okay, so you have lower off current and then higher on current. But what is this? I mean, this is basically the signature of what I'm trying to point to. Can anybody use that term? Slope. Yes. Is it steeper for the green one or no? Steeper slope. So that's why steep slope transistor. NC-FET is a steep slope transistor. You get a boost from the negative capacitance, which makes it steeper. It rapidly turns on compared to conventional standard MOSFETs. And that's how, by making the slope steeper, you reduce the off current and you increase the on current at a given voltage. Make sense? Okay. So let's see whether you get that signature. Because, I mean, this is exaggerated to make a point, right? The one that I drew. When you see the actual data, it will not be as pronounced, but you have to pay attention. Even more reason to observe me as I draw. Take a look at this black line first. This is standard, and it will no longer be black when I draw on top of it, right? So let's see. Start with here, and you go all the way up to this point. This is on current. And why you have the other one? This is for PMOS. So you have NMOS and you have PMOS. Okay, they're basically symmetric for the most part. Okay, look at all the other lines, the red one and the green one. What do you notice here? They have lower off current and slightly higher on current. Does that make sense to you guys? And then, I don't know if it is visible enough, but if you pay attention, they have steeper slope. I mean, it's not as exaggerated as I showed you before, but it is still there. Make sense? Why do you have such minimal change? Because the transistor, baseline transistor that was used here was already too good. So if you take a Ohrs transistor, you can make it really better. And then you see the visible change. But if it is already very good, very close to the Boltzmann limit, the change is not as apparent. But the other reason is it's in log scale, by the way. So the changes are not really that pronounced here, but they change a lot. Am I making sense? Maybe by an order at least. Okay, if you see the ID VDS characteristics compared to the standard, your on current increases. Okay, I see a lot of confused faces, and so I will quickly get out of this negative capacitance business. Okay, don't worry about it. Don't feel lost. That's not the purpose of this course. You'll see where I'm going with this. I cannot explain what I'm going to explain in this slide without going through these two extra slides that I went through. Otherwise, this will have no meaning for you. Okay. All right. So getting back to SRAM. Now, can you relate? Do you feel safe now? We're back to SRAMs. Okay. SRAMs. So what we are going to do is basically one approach. It's not just with NC-FET. There have been a perpetual approach towards changing the transistors in SRAM to make them better. And one of the talks that you'll hear from IBM research, it will be about exactly that. They've replaced the SRAM transistors with something more advanced, something actually one of the most advanced form of transistors in the world. And that's what they can make. And basically, you see the same SRAM argument, but just better. And you're making them better by making the underlying transistors better. Okay. So in NC-FET, you can replace these transistors in an SRAM with negative capacitance transistor like this. And then you don't just get more benefit, you get a unique design opportunity. And that's what I'll have to explain here. See, I had to make a call to select this to be part of the course, right? I have to explain this. I know. I cannot just put, oh, they just become better if you just put NC-FET, done. There you go. But I want to take this opportunity to explain why. Okay, but you have to work with me. Trust me, it's really difficult to explain. And very few people who work on this NC-FET stuff will know. But this is future, folks. If you don't care about, if you only hear about SRAM and DRAM, I'm not doing you a service. Okay, for today it's fine. Maybe 5 years down the line, you'll not really gain much. So you have to worry about, get your heads into something that is up and coming. Okay, so ferroelectric FET, trust me, spintronics, magnetic RAM, STT MRAMs and stuff, and ferroelectric memories, they are getting a lot of attention in recent time. There is a good chance that some of them will be possibly replacing some of some of our existing memory hardware. Okay, so ready to pay attention? Okay, notice when we decide on designing SRAM circuits, which I didn't get into before, you look at both NMOS and PMOS. Okay, and we use something called a load line approach. So if you take ID versus VDS characteristics of NMOS, it looks like this. And then if you plot the same for PMOS, with some excess adjustment, it looks like this. How many of you have ever worked on load line analysis? Yes, some of you. So you know what I'm talking about, right? Sometimes it will intersect here or here. Depending on that, you decide on the mode of operation. Is it going to be saturated? Is it going to be linear? Blah, 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 right? So turns out, I'll try to make it easy. All the conventional MOSFETs will give you one point of intersection. I don't care whether it's saturation or linear or whatever, just one point of intersection. Can anybody tell me a way to somehow create 2 points of intersections? What does this point of intersection mean? It means it represents Q point, which is basically the stable point for the system. So when you have two transistors, NMOS and PMOS connected together, they will stabilize. They will basically make a deal. Hey, I do this, you do that. This is our Q point. So they agreed to be in a certain electrical state, which is stable. So they have one stable state. The entire system can just have one stable state. And that's the Q point that you see here. Where did I draw? Sorry. Yeah, this is the Q point. There could be just one stable state. All right. Now, I'm going to answer for you. What if you had something like this? Okay, I mean, I couldn't do justice, but the point is, if you had a curved ID versus VDS property like this, let's see if I can draw the other one properly. There is a possibility that, do you notice that? When you design or when you work on the load line, there could be multiple points of intersection and even possibly beyond. That means the system could possibly be in multiple stable state, but that doesn't mean they will be all at once. Okay, so when you go from low voltage to high voltage, one of them becomes the preferred Q point. When you go from high voltage to low voltage, the other one becomes preferred Q point. So for one type of sweep, increasing voltage, one Q point, decreasing voltage, a different Q point. For conventional MOSFETs, doesn't matter what you do. If you increase the voltage, decrease the voltage, your Q point is just one. Doesn't matter. One Q point. But it is possible if you had this kind of a curved ID VDS, you can end up with two Q points. Okay. First of all, what am I talking about? Turns out, because of the negative capacitance effect, among other things, what you get here is called negative differential resistance. You know, 335 folks, notice, oh, current is decreasing with increasing voltage. What is that? Is it not negative differential resistance? You get negative differential resistance because of the signature of negative capacitance in NCFET. I'm not connecting all the dots. I'm just jumping, as you can see, hopping from one point to the other. But they are all linked, and I'm happy to sit with you. In fact, I have papers. Like most of these are our papers, by the way. So I'm one way or the other involved. So I'm more than happy to get into the detail, but I'm not trying to scare you off from this course or anything. Okay. The point is, because of this interconnected phenomena, you get negative differential resistance, and they can intersect at multiple Q points like this. This is one possible Q point. This is other possible Q point. And what I'm getting with that is, how many of you remember voltage transfer characteristics of an inverter? Did you draw it enough time in the SRAM lecture? V out versus V in, which was like this. And then for the other inverter, we had to basically revert and get it like this, okay? For NCFET inverter, if you get negative capacitance, this is what happens, V out versus V in. For forward sweep, you get this path. But the same inverter, remember, when I flipped it over, this was inverter 2, and this was inverter 1. So two curves represent different inverters, not the same inverter. For this, if you're dealing with inverter 1, if you're increasing or decreasing the volt, basically it's the same VTC for the same inverter. Okay. But here for ferroelectric inverter, NCFET based inverter, for one kind of sweep, you follow this path. For the other kind of sweep, you follow slightly different path. There is a slight difference. Am I making any sense here? So basically this one, notice, you follow this path or the other path. And this is a signature of one of them being chosen as the Q point here, and the other one as the Q point there. So they choose two different Q points. while increasing or decreasing. Whichever Q point comes first, they choose it. Am I making sense? So for example, when you are increasing voltage, maybe point C comes first, you take point C and behave accordingly. When you're reducing the voltage, point B comes first and you choose point B and behave accordingly. That's how the physical scenario works out. Make sense? And by the way, we experimentally demonstrated these types. By the way, it's not like just theory anymore. Okay, not too long ago, 2017, this paper is one of my highest cited papers, like second highest cited papers ever. So as you can see, this is reality. Right? People have done it. So and this is global foundry. They're an industry. They make it in bulk, like thousands, basically. So not just one fluke. Okay, so the point is, this is a reality. Instead of conventional VTC, you get a VTC which is hysteretic. And here is where things become really, really crazy. Can you guys help me? It's gonna be really, really busy, I know. I chose this. I chose to deal with this, but all right. So this is one VTC. How do you have the butterfly curve now? Well, let me try. For the green one, let me try to make it dot. For the yellowish one, you see, there are too many points of intersections. I don't know which one to take what. Doesn't make any sense, right? So it's very confusing there. So it's basically, this is what I'm talking about. When you take this and flip it over, because of the hysteresis inherently in one of the VTCs, you have multiple points of intersection in the butterfly curve. So the system becomes even more complex. It's a very complex system. What I'm trying to tell you is that for conventional SRAMs, both of these lobes are valid. Okay, and remember, if one of these lobes becomes small and the other one becomes big, does that help you? No, because the smaller one will become the bottleneck now. Remember, we talked about SNMs, and whichever is the smaller one tells you what the SNM is, not the bigger one. So it doesn't make any difference. But apparently, for INCIFET-based SRAM, it's possible to create lobes like this: small, big, and big, small, big, small. I'm giving you the big picture here. But interestingly, because of the multiple Q point nature, only this lobe is activated for one scenario, and the other lobe is activated for other scenario. When you're going from low to high or high to low, when you're charging the node or discharging the node, you always activate the bigger lobe, and the smaller lobe is not even accessed. Making sense? The system can always choose the bigger lobe. And as you can see, I've hopped a lot of stuff here just to get to the end point, because I see always, it's very confusing. Just take a look at this experimental data. So look at the black one. This is really tiny, small lobe. And this is a very big lobe. And this is mentioned as valid lobe. Notice the red one, which is the counterpart. The red one has a really small lobe here and a really big lobe on the other side. So the big one is activated, the smaller one is not. But practically, if I try to draw the butterfly curve, try to visualize it this way. Put the red one on top of the black one in your mind, and then you see the butterfly curve, which, like, my goodness, super complex. So does that make sense to you guys? Okay, that's exactly what we have achieved. We have managed to increase both lobes, which was impossible to achieve in conventional SRAM. If you make one of them big, other one becomes smaller. Make sense? But now, because of having multiple Q points, you always use big lobes, and you can increase both of them individually. Does that make sense? And that's what gives you the, I know I have just 1 minute. Give me like one additional minute, 2 more minutes. I want to finish it up. And no, don't worry, I'm not going to test you on this. I still wanted to touch upon so that you have knowledge on this topic. It's up and coming, okay? All right, so getting back, you now understand why there are multiple Q points. What happens because of multiple Q points? You have hysteresis in VTC. And because of hysteresis in VTC, you have, this is standard SRAM. This is basically what you get during read. This is what you get during write. So one of the lobes becomes smaller and the other one becomes bigger. But for NCFET based SRAM, you always use the bigger lobes here and there. And that gives you tremendous advantage in SNM. Your SNMs will always be bigger. And let me show you realistic data. This is standard SRAM. I hope we could analyze this data together. This is NCFET based SRAM. This is hold SNM. Is higher SNM better or not? Higher SNM means more noise immunity. Okay. So can you notice that why are there so many points? Because did I tell you that there is no one value that I can tell about SNM? If there are millions of SRAM, they will have millions of different SNMs. We have to plot them all and see what? See the minimum, the worst case scenario. Do you see that in this realistic source? This is the minimum. We are looking out for the minimum and the minimum here. So the minimum for the standard and minimum for the NCFET, you have much better SNM in the NCFET stuff. It looks even better, but that's not what we are after. We are after the worst of this. The worst of this NCFET is better than the worst of the standard. That's what you get by making what? By making the lobes bigger. Same applies to read SNM. Look out for the minimum of the standard and minimum of the NCFET, and you get advantage. 40% more SNM and whatnot. What is the technique? There could have been a question. Can you make both lobes bigger? No, you cannot. That was known as the challenge in the circuit design community. So you solve that challenge by going with NCFETs. Okay, so I will leave it. Don't worry, if you don't like it, just forget it. Okay, I'm giving you the license to forget it. So in the next class, we'll discuss the other kind of memory which you cannot forget. This is basically the number 2 in the race for being the next generation memory. So you should care. Okay, all right. Thank you all.